Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good day everyone. So today we are going to learn about the part 2 of the chapter 2, which is diode. And then in this subtopic, in this topic, we are going to learn how to analyze the diode circuit by using two methods, which the first one is a graphical approach and the second one is the mathematical approach. Okay, by using the diode model. And then just to let you know that in this chapter, okay, we are going to learn about the ideal and practical, how to apply the ideal and practical diode by using the mathematical approach, and then the other one is a graphical approach by using the load line concept. Okay, so what is actually the load line concept? The load line concept is actually the relationship, okay, between the current and the voltage in the linear part of the circuit that is represented by the load line. Okay, it is very important to identify the load line. Then after identifying the load line, you have to identify the Q point. The Q point is where the point that is the diode is perform very well and at high performance. Okay, all right. So for the load line, as you can see, okay, for the example, okay, in this example, you have the voltage source, okay, you have the resistance, and you have the diode that are connected in series. Okay, so first of all, okay, whenever you want to apply the load line, it is very important for you to identify the cut-off point and also the saturation region. Okay, what is actually the cut-off point? The cut-off point is when the ID is equal to 0. Okay, meanwhile, for the saturation region is where the VD is equal to 0. Okay, and then after that, okay, how we solve the diode circuit by using the load line is, okay, you need to apply the mathematics. Okay, you need to apply the KVL for this particular question. Okay, to draw the load line, okay, we also apply the mathematical approach as well. Okay, because we want to know the original equation of this circuit. Okay, for example here, okay, when it is connected in circuit, of course we know that the VS, okay, equal to the VR plus with the VD. What is the VD? VD is the voltage across the diode. Okay, what is the VR? VR is the voltage across the resistor. And what is actually the VS? VS is the source. Okay, VS is the source. Alright, so then when we expand the formula, we know that the VS is equal to ID. Why ID? Because we know that the current that flow across the diode is actually similar to the current that across the resistor. Okay, that is why we name it as a ID. Alright, ID and R plus with the VD. Alright, now, okay, now I mentioned just now, okay, we have to find, in order for you to draw the load line, it is very important to identify the cut-off point. The cut-off point is when the ID is equal to 0. So when the ID is equal to 0, what will happen? The things happen is that the VS is equal to your VD. Okay, that is why here we use the VDD. Sama lah VD ke VDD ke sama. We know that for the cut-off point, the ID would be 0 because of what? Because it is at the x-axis. Okay, as x-axis. Okay, and then after that, okay, for you to find the saturation region, what happened? Okay, the situation is that your VD must be equal to 0 because this point is at the y-axis. Okay, so what happened? What happened to your formula? Okay, your answer would be when your VD is 0, okay, your VS is equal to IDR. Alright, IDR. Okay, so then what happened? Okay, what happened after that? Okay, to find the ID, so the VS over R. So this is why, okay, at the saturation region, the VD is equal to, the ID is equal to VS over R. Why the VS is actually the VDD, alright? The VDD. Okay, so now, let's take a look. Alright. Okay, so let's take a look at the example. Okay, when you apply the KVL, okay, into the circuit, this is the answer, right? The VS is equal to ID RL plus with the VD. Okay, this is the KVL. The KVL here, and then the current flow is the ID. Okay, and then, okay, you have to find this cutoff point and this this saturation region. Okay, alright, for you to draw the DC load line, you have to find those 2 points, okay, which is the cutoff point when the ID is equal to 0 and the saturation when the VD is equal to 0. Okay, so if you can see here, okay, the formula from here, when the VD is equal to 0, okay, so you can get the VS equal to ID RL. Alright, okay, and then you can rearrange to find the ID. Okay, the ID is equal to VS over RL. Now, what is the value of the VS? Which is 4. What is the value of the RL? Okay, from the graph, which is the 200. Okay, at the end of the day, you can get the value, the point for the saturation region. Okay, the ID is equal to, okay, equal to 20 milliampere. Alright, what about the cut-off point? The cut-off point is where your ID is equal to 0. So, therefore, from this formula, this general formula, okay, you can get this formula. Because of what? Because of your ID is equal to 0. So, when you don't have any ID, so VS is equal to VDD. Okay, automatically, you can get 4 for the cut-off region, cut-off point, and then you can get 20 for your saturation region. Okay, that is how we solve the load line. Okay, so after that, what you have to do is, okay, you have to connect the DC load line, okay, the saturation region and also the cut-off region, cut-off point, you have to connect. And then the intersection between your diode response, okay, where is your diode response? This is your diode response. And also, your load line is actually your Q point. Okay, usually we refer to VDQ, okay, the best performance of your diode. Okay, the VDQ and the IDQ. Alright, so and then after that, when you get the VDQ and also the IDQ, you can calculate for the resistance by using the Ohm's law. V is equal to IR. So you can get 50 ohm for the static or DC DC resistance. Okay. Okay, so these are the situation where we want to evaluate the effect of the RL. What is the RL? Is the resistance lah, resistance inside the circuit, and also the VS, the source of the voltage. Okay, the source, voltage source on the DC load line. Alright, so there are 2 cases. The first one is when your RL is fixed. Okay, your load line, the slope of your load line is actually indicated the RL. Okay, indicated the RL. Then what happened? Okay, when you change the source, we know that at this point, the cutoff point, the VS is equal to VD. The VD is equal to VS. Therefore, when you change the value of the source, okay, automatically your X point would be different. Alright, would be different. Okay, so what about your ID? Okay, since your ID, since your VS is increased, okay, so ID also will increase according to the load line drawn. Okay, and then after that, for the second case, when you have fixed VS, the voltage source, this one is located when the VD is equal to VS. Alright, alright. Therefore, It's actually the VD, the value. Just follow the value here, follow the VS, the value of the VS. And then what happened when the VS is fixed? So meaning that your cut-off region will not be changing at all. Okay, tak berubah. Okay, yang berubah adalah bila you tukar, when you change the value of the resistance. When the resistance changes, we can say that the slope gonna be changed as well. Okay, that is how we analyze the effect of the RL and also the voltage source in the DC load line. Okay, and then and just now I mentioned the diode resistance is just you apply the V is equal to IR, the Ohm's law. Okay, since you get the VDQ, okay, over with the IDQ, then you will get the value of the resistance. Okay, the DC resistance or the static resistance. Okay. Alright, so this one is the example. Okay, determine the DC resistance level for the diode of figure below. Assume the diode is made from silicon. Okay, alright, so now, okay, we know that the formula V is equal to IR. Okay, in order to get the resistance, you have to find the VDQ, and also the IDQ. Alright, so now for the first question is, okay, when your ID is 2, okay, what is your VD? Which is 0.5, right? So 0.5 over 2 milli. Okay, you will get 250 ohm. Okay, sorry. Okay, 250 ohm. And then, what happened when your ID is 20 milliampere? Okay, 20 milliampere, you get the value of the VD. Alright, and then after that, alright, 0.8 divided by 20 milli, you will get 40 ohm. Okay, this one you just need to apply the basic Ohm's law. Okay, alright, next, this is the solution line. Okay, the diode resistance. Now, let's take a look the how we are going to apply the mathematical approach for this diode circuit analysis. Okay, before that, you have to keep in mind that, as I mentioned just now, there are two types of model. Okay, the first one is the diode model, which is very ideal, okay, where no resistance at all. And the second one is the practical diode. Okay, so for the ideal diode, okay, you can see that the curve, okay, the blue, this one is the relationship between the current and the voltage. Okay, very 90-degree curve. All right. Okay, so we know that, okay, when we connected the positive polarity of the source with the anode, okay, and the negative with the cathode, okay, the negative polarity with the cathode, this one is actually the forward bias. When the forward bias, meaning that the current can flow across this diode. Okay, but then what happened, okay, if we connected the diode in the reverse bias? Okay, when we connect the diode in a reverse bias, meaning that it will act as a switch off. Okay, the switch will be open. Okay, meaning that there is no current will flow. Okay. Okay, so for the practical, we have to include the barrier potential, the voltage of the diode itself, in which when we use the silicon diode, okay, the voltage, the potential barrier would be 0.7 volt. Meanwhile, if we apply the germanium, it is 0.3 volt. Okay, so it is very important for you to consider this value when you want to solve the diode circuit. Okay, when you want to analyze the diode circuit. Alright, okay, so this one, alright, so this one we can see that when we consider for the practical diode, okay, the current will increase when the forward voltage exceed the 0.7 volt. Okay, that is why we have to know, okay, if the source exceeds the value of the knee voltage, okay, knee voltage meaning that inside the voltage, inside the limitation of the voltage across the diode, okay, so we can assume that the diode can be replaced with the battery. with the battery. For example here, okay, we connected in the forward bias. Okay, let's say if the if the voltage source, if the voltage source exceed the value of this voltage, okay, the knee voltage of the diode, okay, so we can we can replace the diode with the battery. Okay, we can replace the diode with the battery. So this one, okay, as I mentioned just now, the knee voltage for the silicon diode is 0.7, the germanium is 0.3. Okay, so now the complete diode model. Okay, voltage is sum of the barrier and voltage drop at the internal resistance. Okay, the voltage changes according to the current value, slightly higher than that for practical. Okay. Okay, so how to analyze the diode circuit? First of all, okay, you have to know that you have to replace the forward bias diode with the relevant voltage source. Okay, so if the circuit is connected in a forward bias, so meaning that you replace the diode with the relevant voltage source. But if it's connected in the reverse bias, okay, you need to change, you need to substitute the open circuit for that diode, and then after that you need to apply the Kirchhoff law and Ohm's law in order to find the related voltage and the current. Okay, so these are the diode, this is the diode specification and the data sheet. Okay, you can refer later on. Okay, so now how we want to analyze the diode circuit for the case of the forward bias. Okay, so let's take a look this one. First of all, okay, we need to set that the resistance inside the diode is equal to 0. Okay, we need to set the resistance. Okay, we can neglect the resistance inside the diode. Okay, since if the VD is silicon, okay, usually it will written lah, it will write, okay, and mention, indicate whether the voltage is silicon or germanium. If, okay, it is silicon diode, so meaning that you need to change with the 0.7 volt. If it is germanium, so you can change with 0.3 volt. This is the value that is commonly used. Alright, so then after that, what you have to do is you have to identify if the voltage source here, okay, exceed, for example, if you use the silicon diode exceed 0.7 volt, okay, so we can proceed with the analysis. But if it is lower, okay, meaning that, all right, so the current is very little. Okay, so now when we apply the Kirchhoff law here, okay, we can get the E is equal to VR plus the VD. Okay, and then the VR we can substitute with the ID R plus the VD. This is the E. Okay, all right. Because of what? Because of the current across the resistance is the similar the current across the diode. Okay, next. Okay, so let's take a look. If it is connected in the reverse bias, okay, you have similar circuit, but the diode is connected in the reverse bias. Kenapa reverse bias? Because the polarity is in different state. Okay, negative with the positive connected with the cathode, and the anode connect with the anode. Okay, the anode is connected with the negative, sorry. Okay, and then since it is connected in a reverse bias, okay, so it is open circuit. When it is open circuit, there is no current will flow across the circuit. Okay, tak ada current yang akan across the circuit. Therefore, the ID would be 0. Okay, and then when you apply the KVL, okay, you can get this equation. E is equal to negative VD plus with the VR. Okay, VR, this one is the small letter, VR here. Okay. Okay, and then this one same, V negative was IDR. Okay, so equal to E. Okay, when your ID is 0, okay, your VD is actually negative. Okay, negative of the source. Okay. Then let's take a look at the example. Okay, the example here. Okay, how to solve this one? Macam mana? Macam mana nak solve? Do you have an idea? Okay, alright. So now, okay, whenever we want to solve the diode circuit analysis, okay, whenever we want to analyze the diode circuit, okay, in terms of whether it is a series configuration or in the parallel configuration, we have to identify whether it is connected in the forward bias or the reverse bias. Alright, so from here we can see this is in the state of the forward bias. Alright, because the positive connect to the anode, and then the negative, okay, connect with the cathode. Okay, alright, so now, okay, by using the KVL, okay, KVL macam mana KVL? 3 is equal to 0.7 plus with the VR. Okay, plus with the VR. 0.7 is actually the voltage inside the silicon diode. And then, what is the value of the VR? Okay, the VR is equal to, okay, tolak je lah, kan? Alright, so VR is equal to 2.3 volt. Alright, meanwhile, your VD, okay, we know that it is 0.7. Because of what? Because the diode used is the silicon diode. Okay, so now, you can see, if it is connected with the forward bias, we can replace with the battery voltage, with the battery lah. Okay, alright, so positive and negative, and then we can solve the equation. Okay, and then after that, now we have found the VD, and what about the ID? Okay, the ID is actually equal to IR, right? Okay, so we want to know how to solve this one. Now, we already have the value of the VR. Okay, the VR is equal to, V is equal to IR, right? IDR. Okay, so your VR is equal to 2.3. Your ID, we don't know the value of ID. And then the R is 2K. Alright, and then you will get the ID is equal to 1.15 milliampere. Okay, we can use the Ohm's law. Okay, because of the IR is actually similar to the ID. Okay, the current flow across the voltage, the current flow across the diode is similar to the current across the resistor lah. Because of what? Because it is connected in the series. Okay, and then, so what about this one? Oh, dah ada answer. Alright, so you can see here. Alright, so now, what about this circuit? Okay, that is connected in the reverse bias. Macam mana? Dia dah connect in the reverse bias. When it is connected with the reverse bias, so automatically the switch is open. Okay, there is no current. Since there is an open circuit, your IR is equal to 0. Because this one, the diode will act as the open circuit when it is connected into the different polarity. Okay, connected to the reverse bias. Okay, therefore, very important for you to identify when you get the when you want to analyze the circuit. Please make sure that whether please identify whether it is a reverse bias or the forward bias. Okay, alright, so now when your IR is equal to 0, okay, by using the Ohm's law, we know that the VR is equal to IRR, right? Okay, so also equal to 0. Then, when you apply the KVL, we know that your VD is equal to negative 3 volts. This one. Okay? Okay. So, next. This one, you can, this one is critical thinking. Okay? So, you can investigate why. Okay? Alright. So light emitting diode is a diode that is designed to emit light. Voltage drop for the LED is 0.8 volt. What happened to the LED when it is connected to the voltage source as in figure A and B and Y? Okay, so you have to connect and you have to relate whether it is connected to the reverse bias, forward bias, and then when this kind of question come out, okay, you have to relate with the fundamental, okay, the electron and so on, okay, the mechanism of the electron when it is connected to the silicon, okay, not silicon in the forward bias, and what is the mechanism when it is connected to the reverse bias. Okay, you have to relate with the depletion region and so on. Okay, that is how you can answer this kind of questions. Okay, all right, so now okay, the diode circuit analysis. Okay, this is the example. Okay, from here, okay, you have the silicon diode, you have the germanium diode as well connected together. So you have to know that the barrier potential for the silicon is 0.7, meanwhile for germanium is 0.3. So you have to include when you want to solve this diode circuit. All right, okay, this diode circuit. That is why when you see here, okay, we replace the diode with the battery 0.7 volt, and we replace the germanium diode with the battery, okay, with the 0.3 volt. Okay, so now how to find the VR and IR? Okay, okay, so in order for you to find the VR is located here. Okay, so you can apply the voltage, the KVL as well. Okay, you can apply the KVL. Okay, so for example, okay, we have the reduction of the voltage across the diode and germanium, and then you can minus with the VR. So 12 minus with the silicon, the voltage inside the silicon, the barrier potential inside the silicon, the barrier potential of the germanium, and the voltage of the VR equal to 0. Okay, so this is the answer. Okay, the 12 minus with the silicon, 12 minus 0.7 minus 0.3 minus VR is equal to 0. Because of what? Because we can find the VR at this point. Okay, so 12 minus 1 minus VR is equal to 0. So 12 minus 1 minus VR equal to 0. Okay, and then you can get, okay, 12 minus 1 is 11. Okay, 11 minus VR. So when you rearrange, you will get VR is equal to 11 volt. Alright, so now done for the VR. So what about the IR? IR, we know that V is equal to IR. Okay, to find the I, you have to divide with the resistance. What is the VR? 11. And then what is your resistance here? 5.6 kilo. Okay, then you will get 1.96 milliampere. Okay, so that is why I told you when you want to apply the mathematical approach, okay, please make sure that you do the revision on the electrical circuit analysis. Okay, the basic one, the mesh analysis, the nodal analysis. Okay, this one is using the node, right? Nodal analysis. Okay, all right. Okay, next. Okay, so how to find this one? Okay, find the V1. Okay, V1. Okay, find the V2. Where is V2? This is V2. And find the V0. Okay, so what is the value of the V1? What is the value of the V0? What is the value of V2? Okay, so this one, I prefer to use the nodal analysis. The nodal. Okay, so let's say, okay, you want to find the V0, right? You want to find the V0. Alright, so now, okay, you have 10 volt minus with the V1, minus with the silicon, and minus with the V2. Okay, my mistakes, Alright. Okay, V2 and minus with the V2 and minus with the negative 5. Alright, so 10, okay, 10 minus V1, okay, minus 0.7 volt, and then minus with the V2 plus with the 5. Okay, so technically, when you want to apply the KVL, okay, it's up to you whether you want to put there are two method, right? Okay, the first one is from higher potential, and then you minus with the reduction of the potential. Okay, and then second one, you also can use the KVL. Okay, yang konsep yang biasa. Alright. Okay, so for my approach, I always do the first one gonna be the highest potential, and then minus with the V1, minus with the V across the silicon, minus with the V2, and minus with the negative 5 equal to 0. Okay. And then you can solve. Okay. You can solve 10 plus with the 5, and then we're going to be 15 minus 0.7 minus V1 and minus V2 is equal to 0. Then you can get the V1 plus V2 equal to 14.3. Okay, so I is equal to R1 plus R2. So technically, since we have the value of the R1 and also the R2, okay, so technically we can find the value of the current. Okay, the value of the current. Okay, now how to find the value of the V1? So since we now have the I, so we can multiply with the 4.7K. Okay, you can get the V1 here. Okay, but how to find the V naught? Okay, how to find the V naught? V naught is located here. So therefore, we need to assume, okay, another loop, another mesh here. Okay, another mesh. So this one you already learned in your electrical circuit analysis. Okay, so you have the Vs. Okay, as I mentioned, the first source gonna be the highest potential, and then minus the V2 and minus with the V naught. Okay, so you rearrange, you can get the Vs equal to V2 plus V naught, and Vs is negative 5. Okay, that's why you substitute here. Negative 5 is equal to V2. What is your V2 just now? Your calculated V2 is 4.56. 4.56. Okay. Alright. So why it is negative? Because this one. Alright. Plus with the V naught. So overall you can get this value. Okay. Alright. So please do your revision. I'm not going to re-explain how to apply all the theory and circuit theory and fundamental in the fundamental circuit. Okay. So you have to learn by yourself. Okay. So this one is the exercise. Please do and please get the answer for this. Okay. Alright. So now, alright, this is the example of the diode circuit analysis for the parallel configuration. Okay, for the parallel configuration, you can see that the silicon diode is connected in the parallel. Okay, so since it is in in the forward bias, okay, so you can just solve as usual. Macam biasa je. Okay, so you know that the VD is 0.7 because of what? Because it is silicon diode. If it is germanium, so you can use the value of 0.3 volt. Okay, so now since it is in parallel, so we can say that the VD1 is actually equal to the VD2. Is equal to 0.7. It is in parallel. Okay, if it is in parallel, so meaning that the voltage value is the same. But if it is in series, so your current value is the same. Okay, so now, alright, so, okay, so your VR is equal to 9.3 volt. Macam mana ni? Macam mana? I give you some time to digest. Macam mana? Okay, so now when you rearrange, okay, you can see that I1R equal to E minus VD. right? So E minus VD minus VR is equal to 0 actually. Okay, you apply the KVL here. Okay, and then okay, you can get the value of this one. Okay, so your I1, okay, your E is 10 volt. Okay, 10 volt. Okay, and then your VD is 0.7. Okay, because of what? Because it is connected in parallel. Again, and then your R is 0.33 kilo ohm. Okay, 0.33 kilo ohm. Okay, so now you can get the I1 is equal to 28 milliampere. Okay. Okay, when you get the I1, okay, now you can calculate the VR. Okay, you can calculate the VR lah. Okay, 9.3. Okay, I1 done, ID1 and ID2. Okay, so ID1 is actually equal to the ID2. Kenapa? Kenapa? Because the voltage here is 0.7. Sama 0.7, 0.7. So, it just divided by 2. Okay, so 28 milliampere divided by 2. This one is the KCL. Okay, so equal to 14 milliampere. Okay, so technically, this is how we are going to apply the KCL, KVL, okay, for the diode circuit analysis. So technically, this one is just like your electrical circuit analysis. Okay, so please make sure that you do some revision how to apply all the fundamental and theories of the electrical circuit analysis in the electronic devices and circuit. Okay. Okay, so in here there are several past year questions. Okay, I hope that you can do. Okay, you can do, and we are going to discuss in the next chapter, in the next class. Alright, so I think that's all for today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.